Hello, here we are again with another lovely session of CENG 4412 Steel and Concrete Design. Alright, continuing on with our Lecture 15. This is going to be the fourth part of Lecture 15, and this is where I'm going to discuss the long-term deflection for reinforced concrete beams. So in part one of this lecture, we discussed how to calculate the immediate deflection for concrete beams, but now I want to talk about how we take into account long-term deflection for reinforced concrete beams. So long-term deflection, RC beams, long-term deflection. And so let's see here, long-term deflection. Well, so we have learned previously that, as I've famously said, that concrete is a wonderfully lazy material. It's a layabout. It's good for nothing. It doesn't work very hard, sort of. It is a lazy material. In other words, it likes to it likes to creep. It likes to shrink. I'm putting videos together too late at night. It likes to creep. It likes to shrink. Those are two separate words, not one word. Crink is not a word. Well, is crinkle a word? I don't know. Anyway, but it likes to creep, it likes to shrink, etc., etc. So, it likes to creep, shrink, etc. So, it likes to shed load, that sort of thing. So basically over the long term, we get additional deflection. We get additional deflection due to shrinkage and creep. Shrinkage and creep. And thankfully, this really isn't that difficult to calculate here. So basically, this is the lambda delta here. Well, this is described in equation 24.2.4.1.1. 24.2.4.1.1. So let me scroll there in my book. 24, or scroll there. Wow. Let's see. Again, so it says here, unless obtained for more comprehensive analysis, additional time-dependent deflection resulting from creep and shrinkage of flexural members shall be calculated as the product of the immediate deflection caused by sustained load and the factor lambda delta. So lambda delta is a factor that we're going to multiply the initial deflection by. Lambda delta is, and the equation for this is going to be psi, or I guess chi here. Well, just xi. Anyway, the Greek letter there. And so it's going to be our squiggle here, there. And basically, all we're going to do is we're going to have a simple formula to calculate this. We're going to run through it, and of course, we're going to get our initial deflection based off of everything we've learned previously. So, in other words, you'll be using the method of transform sections, all that sort of thing, to find the overall final pronunciation. And so, again, this is kind of xi, the Greek letter xi, xi here. If you're not familiar with the Greek pronunciation, xi, or xi. Anyway, if I can manage to pronounce things correctly. And that is going to be divided by the factor 1 plus 50 times root times rho prime. What a lovely Greek equation there. And what are these things? So first of all, our xi here, basically, like xylophone. Looks like I always just kind of draw it as a squiggle. This is kind of just a squiggle here. This is going to be a factor here. Well, let me get that properly. Something more like kind of like that. I really can't write that later to save my life. So something kind of like this. too late at night for Greek letters, or at least Greek letters like that. That's for sure. And this is found in. This is a factor that is found in basically table 24.2.4.1.3. 0.2.4.1.3, and this is basically just a time-dependent factor. So if you're looking at a deflection 5 years out, then it equals then this will equal 2.0. If you're looking at 12 months out, in the 12 months in the future, this will equal 1.4. 6 months, this will equal 1.2, and 3 months in the future, or from, not necessarily in the future, 3 months from the initial loading, 3 months, this will equal 1.0. And then these rho prime, let me put this over here. Rho prime is going to be your compression ratio, the compression steel ratio. So oftentimes this will just be 0. But depending whether you have it or not, rho prime is the compression steel ratio. So again, this is only if you have a doubly reinforced beam, something with both steel and compression reinforcement. So this is the compression steel ratio. And what that means is basically rho prime would be equal to the area of any compression reinforcement divided by the gross area of beam, gross cross-sectional area of compression reinforcement, the total, not the area of one bar, but the total area of any compression reinforcement, divided by the gross cross-sectional area. Cross-sectional area of beam. And really, that's all you need to find the long-term deflection. That's it. It really is that simple. Getting the initial one is the hard part. Okay, so like anything else, though, we're going to need to compare this to something, and we need to find the maximum possible deflections, or the maximum allowable deflection. So here, and let's see here, and this is provided in table. So deflection limits. And this deflection limit, this gives us deflection limits for both short and long term. Deflection limits. And this is found in table 24.2.2. And so here, let's see here. There is a term that we're going to use. Basically, I'm going to sort of simplify this table a bit, and it depends on it depends on a few things: the type of element, the delta considered, the deflection considered, and the limit. And so let me just kind of go down here. And I'm going to use some rough abbreviation for this. The first one would be roofs here, not attached. Roofs not attached to NSELDBLD. What a wonderful terminology, abbreviation. Not attached to NSEL, let's see, DBLD. And what does that mean? Well, not supporting or attached to non-structural elements likely to be damaged by large deflections. So roofs not attached to, or not supporting or attached to non-structural elements, so that's things like walls and brick and drywall and things, likely to be damaged by large deflections. So here, if this is, again, this here would be Again, roofs not attached to any, so not supporting non-structural elements likely to be damaged by large deflections. So here you're looking at immediate deflections, or basically immediate live load. Immediate live load. Immediate live. And I'm looking at just, I guess here, flat roofs. I should mention that's flat roofs. Flat roofs. And this would be, we're considering the immediate live load. And the limit here is L over 180. So the immediate live load applied to this thing, not any kind of long-term deflection. Then if you have floors, floors not supporting the same kind of thing, not supporting, or just not NSELBLD. And really, again, all this is saying is that, and actually, let me summarize. Let me continue this, and I'll summarize later. Immediate live. And you're allowed L over 360 here. L over 360. And so, again, this is not supporting non-structural elements likely to be damaged by this. So in other words, they're not. In other words, there are no. You can use this limit, checking the immediate live, if your floor or roof is not supporting anything that's going to be damaged by big deflections. Like, if your floor is not supporting brittle brick or drywall or something like that, you can use these limits here. Then here, if I want to look at here, the long-term deflections, this is where the long-term come in. And this applies to roofs or floors. Roofs or floors. Roofs or floors here. Let's see. That are supporting, that are attached to, actually let me write this here, put this in here. Are attached, that are attached, attaché, that are attached to non-structural elements likely to be damaged by large deflections. Did I miss a D there? Be damaged, likely to be damaged by large deflections. By large deflections. So if they are, in other words, this is going to be critical where we don't want very large deflections. Here, basically, so what we're considering is that part of the total deflection occurring after attachment of the non-structural elements, which is the sum of the time-dependent deflection due to all sustained loads and the immediate deflection due to any additional live loads. So this is basically the deflection that occurs after you attach the non-structural elements. Attaching non-structural elements. Non-structural elements. And this is because this is going to be more stringent and vulnerable to damage, we have a much lower limit of L over 480 here. And then if you have roofs/floors not supporting these, or roofs/floors supporting attached to non-structural not likely to be damaged by deflections, elements not vulnerable to damage by deflection, vulnerable, I'm kind of rewording this, to deflection damage, deflection damage, if I can not scroll to the next page, that'd be good. Deflection damage here. And again, this is the delta after attaching non-structural elements. Here, same thing, delta after attaching non-structural elements. Non-structural elements. And here, this is where you'll have, this is going to be used L over 240 here. So here, let's see. Let's see. So again, this says the part of the total deflection occurring after the attachment of non-structural elements, which is the sum of the time-dependent deflection due to all, again, which is the sum of the time-dependent deflection and the immediate deflection due to any additional live load. And that takes into account things like ponding and etc. So, well, actually not for ponding for that one, but you can read the commentary therein. Basically, this is this includes, so these long-term ones, those bottom two rows include two things. You can read up on this, but basically the bottom two rows contain two things. Rows contain two things. One, and I should say this is delta considered immediate deflection from max live load. From max live, and the same thing, immediate deflection from max live. It's not just live load, but immediate deflection from max live. From max live. And I really want to parse this this next one critically. The bottom two rows contain two things. One, that part of the total deflection occurring after attachment of non-structural elements, which is the sum of the time-dependent deflection. Basically, it's time-dependent deflection. Dependent deflection. Deflection. Let's see, which is the sum of the time-dependent deflection due to all the sustained loads and the immediate deflection due to any additional live load. Due to the time-dependent deflection from any sustained loads, so the time-dependent deflection, just the time-dependent deflection from any sustained loads, and the immediate deflection that's not where that C goes, due to any additional live loads. So sustained loads would be things like dead loads, or drywall, that kind of thing, drywall, brick, windows, etc. To live loads. You're not going to usually be concerned with the long-term deflection of live loads, like I see, unless you have a heavy piece of equipment sitting in one place for a long period of time. But again, so here, and crucially, this is just the deflection. So for example, this is just the deflection from the long-term deflection of that, of the dead load basically, and the short-term deflection of the of any live load present. But anyway, I think that'll do it for this here. But basically mainly from dead load. So, and you can read more about that in the commentary, but I hope that gives you a brief introduction to long-term deflection. So basically, you do not need to consider, so this does not include the deflection from, this doesn't include the deflection from initial dead weight, but basically, you're just using the formula addition. So if you look on the equation 24.2.4.1 that we discussed previously, this actually the verbiage actually meshes nicely here. It says, unless obtained from more comprehensive analysis, additional time-dependent deflection resulting from creep and shrinkage of flexural members shall be calculated as this. So basically, you use your lambda here, multiply it by the initial deflection, and you compare it to this here. And you compare it to that there, plus adding any live load. So again, let me summarize this. So for example, if you have how to apply, for example, the last row. One, calculate, generally here, this is kind of a rough explanation, your lambda delta you calculate your lambda delta. 2, multiply this by effectively your deflection dead, because that's the only one that's really going to increase long term, because that's the only sustained load that's really present, and then add this to your lambda live. So really what this kind of comes down to is that for the last row here, for example, you'd basically be using the equation lambda delta times delta D plus delta L, any instantaneous live loads, must be less than or equal to L over 240. That would be a rough estimate or a rough explanation of how you might use an equation like that. All right, so I just want to provide you that explanation. Hopefully that clears things up of how to handle long-term deflections for reinforced concrete beams. All right, thank you for watching, and I hope you enjoyed this video, and as always, thank you.